But it's okay, I'm alive. And I do have future. Thanks, God.
I'm glad like you hear that. So I'm getting anything else.
So it must be a red eye flight
Yeah.
to get there in the morning.
Mhm.
Yeah, usually when you fly to the East Coast, that's what they do.
Yeah, so it's gonna be like rough.
I actually think it's harder flying home when you come back west, because then the day goes forever and you're like, you get back and it's really not very late, but you've been up for many, many hours. Everybody else is like, still kind of halfway through their day, but you're like,
Yeah.
really tired. But when you go over there, you just kind of sleep on the plane.
That's what
and-
I'm hoping to do.
Yeah, and then, yeah, it usually works out pretty well that way, I think. Okay, guys, I think I'm gonna go ahead and get started here. Welcome to another Math 471 day. I wanted to just remind you, if you happen to be around tomorrow, I know Fridays are sometimes different schedule for everybody, but I am actually giving a talk in the problem solving seminar that you might be interested in. Problem solving. And that is from 1 o'clock until 1:50. So it's just 1 hour basically. And it's in this room, which is MH 476. And I am going to be talking about sort of problem solving in the context of combinatorics. I've just chosen to do that. I mean, I've given talks in this seminar before on other branches of math, but I thought, well, I'm teaching combinatorics, so I should give a talk about problem solving in combinatorics. And in particular, I'll probably do some examples from some of the math competitions that sort of have inspired this seminar to be in existence. So the Putnam exam comes to mind, but sometimes you'll find that, I mean, combinatorics is a fairly, widely discovered thread through a lot of different mathematical. So you may actually, as I've talked about many times, be able to find combinatorics problems at a much even lower level. It doesn't mean that they're easy problems, but anyway, I'm going to give a 50-minute little spiel about that. I'll probably solve a couple of problems. And if you're free and want to come, I'd just like to invite you. It's certainly not required, especially because it's on Friday and people may have other things to do on Friday, but I will be here tomorrow afternoon at 1 o'clock. Yeah, so just wanted to get that out there. Second thing, I would like to remind you that there's a homework assignment due tonight, and I will be around after class today, starting at 5:30, and I'll be around pretty much all night, with the exception of a little dinner break. Probably a little bit after 7, I'll head out for about an hour or so. Other than that, I should be around. I'll be in Zoom, I'll be in person. Definitely feel free to stop by and ask questions if you have any. I'm always happy to help, and we'll try to do so. I do have a new assignment already for you as well for next week. That's on some of the graph theory stuff that we're just going to be getting started into now. I want to thank you all for, I know it was somewhat short notice to kind of watch that video, but I was a little nervous last night. I went to bed, I saw, oh, gee, only half the class has done this. I hope people are going to know what I'm talking about. But then I just checked a few minutes ago. It's like I think everybody's pretty much done it. So that's great. Thank you for watching that video and taking notes. And I hope that it mostly made sense. I'm going to do a recap of the video kind of today. So totally new topic. We will be doing, this is week 9, I think. We have about 5 or 6 weeks left. Most of those 5 or 6 weeks we will be spending on graph theory. We're going to be, of course, exploring graph theory from a mathematical perspective, from a very theoretical point of view. After all, I am a pure mathematician, right? So, of course, graph theory has many applications. Computer science, building highway systems and building plumbing systems for a neighborhood of homes. There's a whole bunch of practical applications of graph theory. I save a lot of that for the engineers, for the computer scientists, and we're going to be more interested in graphs in their own right, what we can discover about them and understanding them from a very theoretical perspective. That's really the aim of a class like this. So there will still be proofs. We may draw some pictures in our proofs now, but it's still going to be very theoretical minded. So I'm going to recap briefly that video that you guys watched. And again, thank you for doing that. That really helps with our timeline going forward. Essentially, I'm just going to give you a quick overview of what you've already watched in the last couple of days. A graph, well, it's a set of vertices and a set of edges. It's really what it is. If I tell you all the vertices and I tell you all the edges, you could pretty much draw the graph. There wouldn't be any mystery about it. And we use V for the vertex set and we use E for the edge set. Each of them is just a set of objects, right? And I usually will draw the vertices as dots and then the edges are just the, well, they're just the line segments connecting some of those dots, right? So that's a graph. More precisely, it's a simple graph. Simple graph is a graph where you don't have any loops and you don't have any multiple edges. So you only need to make one edge, at most one edge between any two vertices, right? So that's a simple graph. We can also talk about general graphs, right? I mentioned that here where you do allow for loops and multiple edges and things like that. So keep that in mind. The order of the graph, well, that's just how many vertices does it have, okay? That's the order of a graph. The graph that has the most possible edges for a given order, say order n, this is called the complete graph, and it's denoted with K sub n. That just means you're drawing every possible edge between every two vertices. They take any two vertices, there's got to be an edge there. Okay, and so how many edges would there be in such a graph? Well, that's where you just say, well, out of the n vertices in my graph, how many ways could I choose two of the vertices? And that's totally the same as how many edges you could draw, because you're drawing exactly one edge between every pair of vertices. So there's a perfect correspondence there, and that's the maximum number of edges that you could have if it's just a simple graph. Okay, where you don't have multiple edges. Okay, we can also talk about the degree of a vertex. This is just how many edges are sort of coming out of that vertex, right? It's the number of edges that are incident with the vertex V. That's the degree of V, and I denoted that here, DEG of V. This handshaking theorem is quite nice, as I talked about in the video. It's just if I add up the degree of all vertices of the graph, what I have to recognize is that every edge does a +1 on 2 of the degrees of 2 of the vertices, right? Because, you know, whichever vertices are incident with that edge will have their degree increased by 1 due to that edge, right? So every single edge contributes 2 to the total degree of the whole graph. So that's where this idea comes from here. And it's kind of nice because, okay, so if you add up the degrees of all the vertices of a graph, you have to get an even number. Okay, so if it's an odd number, well, then it would not be in a correct graph. There would have to be something wrong with that. Okay, so that's one of the early theorems in the subject of graph theory, this so-called handshaking theorem. Okay. Right. There were some other things in the video. There was the idea of a planar graph. This is just a graph that you can draw without any edges crossing over each other. Sometimes that might require you to redraw an edge so that it stays outside of some region that's going to be crossing another edge. Okay, so we're going to talk more about planar graphs later. That's not really what I want to focus on here, but that was in the video. What else was in the video? Well, there was also a discussion about things like walks and trails and paths and cycles. It's a lot of words, pardon? Hikes and jogs, right, exactly. All the things I care about. So of course I enjoy it. I do think it's a little heavy in terminology. So what's the difference between versus a walk? A walk is just any consecutive sequence of edges in the graph. So that's like the most general definition. Everything is a walk. If you just start at a vertex and just start following the edges, I don't care if you revisit the same vertex. I don't care if you walk across the same edge again. Doesn't matter. That's a walk. Then you get into things like paths and trails where you're not allowed to repeat certain parts of the graph. So I'm not gonna write all of those terminologies down again right this minute, but that would be worth, that might be flashcard worthy. There were a lot of definitions in that section of the video. Well, there were really quite a few definitions overall, so it wouldn't be a bad idea to maybe draw a few flashcards out with those definitions on them. But we're going to be studying, even today, I'm going to talk about something called Eulerian trails. So this concept of a trail is going to come back up enough that you're probably going to learn it through just the intensity of going over that material a fair bit. So anyway, I didn't put it into the recap of the video. I don't want you to think this is a comprehensive review of it, but it certainly gets a lot of good points down. The last part of the video was about graph isomorphisms, and that's kind of where I'm gonna try to pick up with today. But before I do that, does anybody have any other questions from the video as you were taking notes on it? Did you discover anything that was bizarre or that you didn't understand, or? Because I'm happy to take a moment to do that. Nikolai? Remember you were talking? Okay, I'm gonna do that here, yeah. Yeah,
Like the second one, like they're obviously the same. I understood that, but second one would be planar, right? Because there's like a cross of the two edges.
so you're talking, let's just make sure we're talking about the same thing. So this is the these are the two pictures?
Yeah.
So you cannot say, because these graphs, they are isomorphic. And I have to review graph isomorphisms, so you're a little ahead of me on that part. But if we assume everybody's okay with that concept, these are isomorphic, so they are both planar or they're both not planar. This would be not a planar representation of the graph. Doesn't mean the graph isn't planar, it just means it's not drawn correctly to show or to exhibit that it's planar. Yeah, was that kind of your question?
Yeah, I was
Yeah.
just thinking, like, would you say that two are isomorphic only if they're?
Well, if two graphs are isomorphic, then they have to share the planarity property, meaning they're either both planar or they're both not planar, right? So it can't be one of them is and one of them isn't. Yeah. Almost any concept that was in that video, whether I think I also mentioned connectedness in the video, existence of trails or paths or whatever. If one graph has loops, the other graph has to have loops, right? Anything that was in that video could be thought of as like a structural property that would be preserved by an isomorphism. I might make a list. I might put that list back up here again in a moment. And we're not even done with the list because we just started graph theory. We're going to have so many more properties to add to that list later on. Yeah. But yeah, so again, I've got it here just in case anybody needs to kind of refresh their memory about this. Two graphs, G and G prime, they will be isomorphic. That just means that there would be a bijection between the vertices. Right away, that means the two graphs have to have the same order, because you can't have a bijection if the two vertex sets don't have the same size. So the graphs have to have the same order, but there's a bijection. But more than that, this bijection has to preserve edges. Okay, so if there are two vertices X and Y, if they are joined by a certain number of edges in one of the graphs, then when I look at the images of those points under this graph isomorphism, so theta of X and theta of Y, those two vertices in the second graph would also have to be connected or joined by K edges. So K could just be one. Right, it could just be there's one edge here and there's also one edge here. But yeah, that's you know, a kind of a difficult condition to check directly and brute force wise on a graph, but that's what the definition technically is. the way we're generally going to play the game with graph isomorphisms is I'm going to give you two graphs. I'm going to ask you, are they isomorphic? Now, if they are isomorphic, I am probably just going to ask you to give me the theta, this actual bijection that you have in mind, okay? Of course, we should check that the theta really does work and preserves edges and non-edges, but that's mostly just an exercise in looking at the pictures. So there won't be a lot to write down other than just what is theta, like what is the correspondence of the vertex sets. That's mainly what you have to do. In terms of if the graphs are not isomorphic, then generally the approach that we will want to use is to look for some structural difference between them. One of these invariants, we call them graph invariants, that must be preserved between, if two graphs were isomorphic, it would be preserved, such as planarity, right? So two graphs, if they're going to be isomorphic, then they have to agree about whether they are planar or not. Either they're both planar or they're both not planar. Right? And if you can convince me that one of them is and one of them isn't, well, then the graphs cannot be isomorphic, you see. So let me just remind you, because I did make a list, but I want to actually write it down one more time, and then we're going to do some examples of this. So just as a quick remark here, this is just, you already have this in your notes from the video, but I'm just going to put it down again one more time. Isomorphic graphs. Graphs that are isomorphic, they must share structural properties. Okay, they have to kind of agree about all of their structural properties. So, for example, I'm going to make a list here. The size of the vertex sets, they have to agree, right? So this should already be in your notes. The size of the edge set. So the number of edges, the number of vertices, right? Our two graphs should completely agree about that. There was another idea in the video of writing down the degree of all of the vertices as well, right? And we can do that in both graphs, and those degree sequences, as they're called, those degree sequences would have to agree, right? So if I look at all of the degrees of all the vertices, I do that for both graphs, they should comprise the same collection of values. And we write that out in the degree sequences of the graph. So that's very good. I mentioned a moment ago connectedness. If one graph is connected and the other one is not, then they're not isomorphic. Connected, that was also in the video, just to remind you, I won't write it down again, but this just means any two vertices can be, you can walk. You can take a walk from any vertex to any other vertex in the graph. It might be a long walk, but you can find some way to do it. Okay, so that's connectedness. The next one is actually a very commonly used one, number 5, which is existence of cycles. A cycle is just exactly what you think it is. You know, you start at a vertex and you take a path that ends up back at that vertex again. It's like a closed walk, essentially. And I'll just say of fixed length. So if we have cycles, that we can actually refine that statement and say, well, if one graph has a cycle of length 7, then any isomorphic graph would have to have a cycle of length 7. It's not hard to understand that if you really realize that an isomorphism is going to have to preserve edges. So in particular, it will preserve a cycle. It will preserve an entire cycle. Seems reasonable, right? The next one is kind of just a generic comment. Again, this is already in your notes, but just to reiterate, relationships between vertices of certain degrees. This is a little bit of a loose statement, but so the degree sequences of my two graphs might be the same, but if all of the vertices of degree 3 are connected to each other in one graph, But in the other graph, they're not connected to each other. In other words, they're not adjacent. Sorry, adjacent is the word I meant to say. If all of the vertices of degree 3 are adjacent to each other in one graph, but they're not adjacent to each other in the other graph, well, then the graphs are not isomorphic, even though the degree sequences might be the same. Okay, so that's something else you can say. And then I put at the end of the list here, I put planar. We've already kind of addressed that a little bit. But the main thing I want to kind of do here, guys, is point out that this is really a ... on this list, because this list keeps going. Later in the semester, we're going to talk about the chromatic number of a graph. And then we're going to talk about the chromatic polynomial of a graph. We can talk about the number of connected components of a graph. We can talk about existence of Hamilton cycles, which we don't know what that is yet. But there's a whole bunch of additional things that we can write down here. So this is kind of a work in progress, is my point. There's just so many more things that we can add to the list, and we'll add to the list as we kind of go along. What do you think? Everybody kind of got the general idea? We need to practice this thing a little bit, I think, today, but are we kind of getting the idea here? Yeah. So what would not be a structural property would be things like the names you gave to the vertices. So if I labeled the vertices of the triangle ABC and you labeled the vertices of the triangle XYZ, same shape basically, we would not say that that's a structural property, even though we used different names. Yeah, the graphs are still isomorphic. Okay. The other thing that's not a structural property is just how you represent the graph. So if I draw the triangle looking like this, right, and then somebody else draws a beautiful equilateral triangle. Okay, again, the exact shape of the triangle is not what's important here, right? You would consider these isomorphic, you know, you can stretch the vertices and reposition them around so that, you know, this one then could be like right on top of this, and that would be acceptable. Yeah, Nikolai?
I think you mentioned in the video that edges don't have to be straight.
They don't.
So does that mean you could draw that triangle as like a circle?
Oh yeah, definitely. I could draw this, you know, differently. I could draw it like this. Same exact, we would, you know, graph theorists would not consider those different at all.
It's for sure a triangle.
Yeah, exactly. So there you go. You can go tell your geometry professors that this is a triangle and this is a circle and that Dr. Annex proved.
I can.
I'm pretty sure.
Tell Rafa.
He'll love that, won't
Yeah, he's gonna agree. You know,
he? He's,
You're like,
nobody's gonna disagree with me about math. So. I've been here longer than that guy. He's got. No, I have to stay on, no, he has to stay on my good side. I try to stay on his good side too, though. I try to stay on everybody's good side. So I don't know how well I succeed at that, but I try.
They play basketball.
No. I don't know that, I don't play.
Yeah.
I mean, I haven't played that much with the faculty. Okay, let's practice, guys. I want to practice on these graph isomorphisms. Let's do a few examples here. So example, I think, you know, I didn't really do much of this in the video, so let's try to actually take some graphs. Are these, meaning the graphs I'm going to draw in a moment, isomorphic? So are these isomorphic? Let's see. I'm going to draw a couple of graphs here and then we'll talk about it. So the first one is going to be basically, and I'll try to go slow so you have time to draw all of this out, but you're going to start with a square. And then there's going to be one more vertex in the center of the square. And I'm going to draw a line kind of diagonally through that central point on one direction, but then on the other diagonal, I'm only going to draw half of it. So I'll draw it like so. That's the first graph. And then the second graph, I'm going to draw it right next to it over here. The second graph, I'm going to try and draw it like a pentagon. So I'll draw a five-sided figure here, like that. And then I'm going to create a few more edges going across like so and like so. We could have something like that. We'll give everybody a second to get that drawn on their notes so we can talk about it. The question is, are they isomorphic? One thing I would mention is that if they don't give you labels on the vertices, knock yourself out and go ahead and put them on there, right? You would want to have labels here. So I could label, A, B, C, D, E, like that, for example. And then on the other one, I would maybe use numbers instead. 1, 2, 3, 4, 5. So labeling the vertices is a good idea, especially if you're trying to write up a homework assignment. You want it to be clear what you're talking about. So as I said a moment ago, if they are isomorphic, we should exhibit this bijection theta, right? But if the graphs are not isomorphic, then I'm going to try to find some structural property that's different between the two graphs. So the question here, so you have to kind of know ahead of time. You have to have at least a gut feeling which way you want to go with this. Do you think it is true that they're isomorphic, or do you think it's not true? Does anybody have a, well, let's take a vote. Let's take a vote. How many people think that the graphs are isomorphic? Raise your hand if it looks to you like they are. Okay. How many of you think that these two graphs are not isomorphic? Raise your hand. Okay, and we have a bunch of people not voting. This is election season, so make sure you get yourself registered, sign up to vote. But yes, so for sure, there were more people saying that the answer is no. So if the answer is no, it's easy to talk about. It's easy to talk to the people who say no, because all we have to do is come up with a structural property. Could somebody tell me what would be somebody who voted no want to give me a structural property that would tell me why it's a no? Amber, is that your hand? Degree sequences. Can we look at that? Let's take a look at the degree sequences. So the degrees here on this first graph, I have a 3, a 2, a 3, a 3, and a 3. Right?
Just on number 2 alone, you know.
Exactly. So the degree sequence 3, 3, 3, 3, and 2, right, for the first graph. And on the second one, I have a 4, obviously, and then a 3, 3, 2, and 2. So the degree sequences don't match. Degree sequences don't match. Okay, so they're not isomorphic. That's good to see. And I got an idea that that should be the case. Okay, let's, is everybody okay with that? It's not necessarily the only structural difference, but if you can find even one structural property that is inconsistent between the two graphs, you can stop. You can just write that down and stop. Let's try another one. Let's practice another example here. So are these isomorphic? So I'm going to draw 2 more graphs. This time I'll start here at the top with a vertex, and I'm just going to go kind of around a hexagon. I'm going to make this hexagon shape here, like so. And then I'm going to make a big X through the middle of it. So I'm going to draw a big X going across like that. Okay, and then for my second graph, I'm going to draw the same hexagon again. We'll get the same hexagon going, but this time, instead of drawing a big X through the middle of it, I'm going to draw 2 horizontal lines through it, like that. Okay. Now, some of you might be thinking, I wonder if we could use the planarity property. And do you think that would be the case? Or can I use that as a reason? This one certainly, remember, planar just means no crossing edges, or that it can be drawn with no crossing edges. So this one's already for sure planar because it's already being drawn that way, right? This one does have crossing edges in it, but that doesn't mean that it's not planar.
You do like a circle.
So I could like take one of these parts of my X that I had, right? And I could like redraw it out here. right? So both of these graphs are planar. They are matching up with that property. Okay, so that would not be a reason. That doesn't mean the graphs are isomorphic. It just means that they do share that particular property. So if I'm looking for a reason to say that they're not isomorphic, that wouldn't be it. Okay, so let me give you another minute here to look at these two graphs, and then maybe we'll take another vote and see what folks think about that. Obviously, you know, they've got the same number of vertices, same number of edges. That's pretty straightforward. Looks like every vertex has degree 3, I think, in both graphs. No, that's not true. The top and bottom vertices have degree 2, but the 4 that are on the sides, they have degree 3. So I think they'd have the same degree sequence. So they're definitely sharing a lot of properties. They're obviously both connected. So far it's looking pretty good. So let's take a vote. Why don't we do this again? Raise your hand if you think maybe this time they are isomorphic. Okay, we got a few folks with the hands up on this one. Why don't you raise your hand if you think that they are not isomorphic? This is very close to 50-50. Okay, got about 50-50 again. So it's always easier for me to talk to the people who say no, because if you're telling me no, then you should be able to give me a structural property. Did you say no?
Yes and no. I'm trying to look. My reasoning is I'm trying to look into the existence of like the cycles of the fixed length.
Cycles, okay. What do we know? What can you tell me about the cycles on these graphs? Is there anything that would help us to, Fernando?
I'm just thinking like on the right hand side, give you like a cycle of size 3, like.
Yeah, and again, see, this is where I should be labeling the vertices so we can actually talk about it. So maybe I should do that first. So we have like A, B, C, D, E, F. And then on the right side, 1, 2, 3, 4, 5, 6. All right. So Fernando's point is that we can look at cycle lengths. And on the right, you were talking about cycle of length 3, right? So the graph on the right, we have a cycle of length 3. And it would be a good idea whenever that is the case, something like that, that you actually write the cycle. So I don't mind on these cycles if you just sort of show me what the edges are. So if I start at 1 and then I go to 2, and then from 2 I go to 6, and then from 6 I go back to 1. So there's a cycle of length 3 right there up on that triangle at the top. Okay, but what about the graph on the left side? Does the graph on the left side have a cycle of length 3? Yeah, you know, you can only make cycles of length 4 and 6 on the left side. So on the left, let's just say we have no cycles of length 3. So actually, later on, we're going to talk about the concept of a bipartite graph. That's another structural property, and it's related to even and odd lengths of cycles. And so we would be able to quote that later on, but at least for the time being, the answer here is no. And that's because, yeah, on one of the graphs, there's a cycle of length 3. The other graph, there's no cycles of length 3 at all. Now that can just be observed. If you're sitting here thinking, well, how do I prove that the first graph has no cycles of length 3? We prove it by looking at the graph. There's not anything to write down for this. You can just simply state it. Now, later on, we're going to have a concept of a bipartite graph, and we'll be able to give a bipartition of this first graph. And whenever a graph has a bipartition, it can't have any odd length cycles. So we will be able to give maybe a slightly more rigorous discussion of this later, but for the time being, you would just simply say, yep, there's no cycles of odd length in that graph. Yeah, Maria?
So for when you're talking about when I
Mhm.
redraw it,
Yeah.
we don't have to like think about that with like the cycles, right? Like, oh, if we redrew it,
It doesn't change your cycle.
Okay.
Yeah, if you redraw the graph just by moving like this edge outside, that does not change anything about well, any of the properties of the graph. So it still has no 3 cycles in it.
Okay, thank you.
right? Yeah, makes sense, Nikolai?
And I had a question that was kind of similar to this.
Uh-huh.
I was comparing it kind of to that first box where, sorry, the square that we
Mhm,
had at the
yeah.
start, where you could flip the two sides.
Oh,
It was the very first example.
yeah, I'm sorry, yeah, this one, uh-huh.
So it's like, I was trying to think, if you could do that with the middle cross and the box with this example, then that would mean that they were. Right. But like the fact that they're connected by one or a and B,
Uh-huh.
do that flip on one side,
Right.
but that was my reason.
Yeah, that would also be fine, yeah. Mhm.
Is there a way to say that
Um,
better than how I said it? Though? I feel like it's-
I would have to, I would have to think about that a little bit. Yeah, it might take me a minute to figure out how to wordsmith that as well. Yeah, Jose?
Been thinking about like the part, right?
Okay.
And then like if we draw like the graph, right?
Mm-hmm.
Then our existence, like the cycles are not unique, right?
Right, the cycles are not unique, but when you redraw these graphs, right? When you move this edge outside of here, you're not changing anything about the cycles or any of the other properties of the graph for that matter. The number of vertices doesn't change, the number of edges doesn't change, the cycle lengths don't change, connectedness doesn't change, planarity
Yeah,
doesn't change.
yeah.
Nothing changes when you simply redraw an edge in a different place. The physical rendering of the graph is not a structural property, right? So if this would be considered a physical redrawing of the same graph. Right, we're not structurally changing it at all. Yeah, okay, let's do one more of those. And then we've got some group work for you guys to try a few of these as well. Okay, so here's another one, another example. Are these isomorphic? Okay, so I'm gonna draw two more graphs over here. See if we can think about this one. So the first graph, I'm gonna have 4 vertices kind of on the top row here. And then I'm gonna draw 4 more vertices on the second row, kind of right below those. So that's a total of 8 vertices here. And I'm going to connect some of the vertices from the top row to some of the vertices from the bottom row. So you'll have to just kind of look at my picture here and just draw this picture in the same manner. I'll label these vertices in just a second as well. So it's going to have all of these edges here. Okay. Make sure, one way to make sure that you've drawn the graph correctly is that every vertex should have degree 3 by the time you've got that drawn. So I'm going to label the vertices of this one A, B, C, D, and then on the bottom row, E, F, G, and H. So we would have that as one graph. And then I'm going to come over here and I'm going to draw another graph. The second graph is just going to be, I'm going to put two squares kind of inside of each other. So there's a square. And then I'm going to make another square kind of outside of the first square. Okay, so connect that up. And then what I'm going to need to do is connect the corner vertices, the corresponding corner vertices of each square. So this is what the second graph would end up looking like. And I'll label this one as well with some numbers here. So I'll do maybe 1, 2, 3, and 4 on the outside corners. And then we'll go around on the inside and put 5, 6, 7, and 8. So those are my 2 graphs that I'm going to ask you about here. If we kind of look at our checklist for a minute, obviously both graphs have 8 vertices. without actually counting all the edges, I can see that the degree of every vertex is 3. So using the handshaking theorem, if I add up 8 times 3, there would be the total sum of all the degrees of the vertices would be 24. That's always double the number of edges. So there should be 12 edges. Both graphs have 12 edges. Okay. The degree sequences, obviously, they're just 3 for everything. So there's no difference there. Obviously, both graphs are connected. And those are the easy things to look at. I find the one about planar to be kind of interesting because the second representation is clearly planar. No crossing edges here at all. But then if I look at the first graph, oh my goodness, the number of times that the graph crosses over itself is massive. So, you know, if these were going to be isomorphic, then obviously this graph would need to be, I mean, that means you can really redraw these edges and get rid of all those crossings. But that seems like that'd be a big job to do that. Relationships between vertices of certain degrees, we could think about that a little bit as we go along here. And also cycles, I don't see any 3 cycles, but I do see some 4 cycles here. And I could probably make longer cycles of maybe 6 or 8, something like that. Does anybody have a gut feeling about this one? This time I won't take a vote because it's maybe something that takes a little more time. But they seem to agree in a lot of respects. Probably not terribly obvious, but believe it or not, these graphs are isomorphic. Even though the first one has so many crossing edges and the second one doesn't, they actually are isomorphic. The way that you can try to convince yourself of that would be to see if you can start constructing this bijection. Now, see, if you start trying to construct it and things go south right away with that, if it doesn't work out very well, then that can lead you to a structural difference between the graphs. So we might discover that in the process of trying to set up this isomorphism. But so just to get this going, I'm going to try to make a theta here. And what I notice, for example, is that, it's basically going to be 2 columns. One column is going to be A through H. The other column is going to be the numbers 1 through 8. And what I'm going to notice, for example, do you see how A, B, C, and D, none of those are connected to each other, right? Completely disjoint. So the A, B, C, and D, they should be matching up with, since there's no edges between them here, then there should be 4 vertices over here that have no mutual edges between them. So do you see an example of 4 of the vertices on the right that have no edges between them whatsoever? So let's put 1 over. So I don't necessarily know exactly how I'm going to match these up yet, but I know that somehow I could put 1 down, and then I need to put other vertices that are not connected to 1. What would be an example of that? 3 and 6 and 8. That's exactly right. So 3, 6, and 8. So this set of vertices A, B, C, and D should match up with 1, 3, 6, and 8. Roughly speaking. Yeah.
Why not 7?
Well, instead of which one of these? See, 7 is connected to 3, and so if you put 7 here, then you have to take out 6 and 3. And if I take out 6 and 3, then I got to put something else in there for 6 and 3, and it's going to be something that's connected to 1, for example. So it's going to end up not working out.
Okay.
It's maybe, it takes a moment to sort of play with that, but yeah, that's basically this vertex, this one, and this one. have no mutual edges between them. Whereas if I put 7 in the pile,
And 8 and 6 can be.
then 8,
Or
6, or 3 couldn't be.
Okay.
Yeah, so we'd have to get rid of all of those and like scrap everything. Yeah. Okay, so, kind of without loss of generality, I'm gonna just try to create an isomorphism by starting, I'm gonna send A to 1 right away, okay? And then I'm gonna look at the next vertex over, which is B. Right? And so B has to get sent to something else that's here. Right? Now I could send it to 3, or I could attempt to send it to 3. But I have to be a little bit careful because, so if we look at what A is connected to, A is connected to F, G, and H. B is connected to E, G, and H, right? So did you notice that A and B, they're each connected to 3 other vertices, 2 of which are in common. So we could ask that about 1 and 3. Are they both connected to, they will both be connected to 3 other vertices, 2 of which should be in common, and then the third one is not. So 1 and 3 are both connected to 2 and 4, right? And then there's one that they're not connected to. It's like 1 is connected to 5, which 3 isn't, and 7 is connected to 3, which 1 isn't. You with me?
Yeah.
So the 2 common vertices for 1 and 3 were 2 and 4. And what were the 2 common vertices for A and B? G and H. So G and H, I'm going to come down to the end here. The G and the H have to somehow go to either 2 or 4, or I'll just say 4 or 2 as such. Okay, so we'll come back and figure out in a minute. Maybe we can do that arbitrarily. That's possible. What is the vertex that A is connected to that B is not?
Right.
That would be F, right? So let's think about theta of F, because F is connected to A, but not to B.
That's fine.
So then that means what is 1 connected to that 3 is not connected to? 5. Exactly. So that would mean theta of F would have to be 5 by that reasoning. Okay, and then what is the vertex that B is connected to that A is not? Remember, these two, they were out of the 3 vertices they're connected to, G and H are common, but A was connected to F, while B is connected to E, right? So the B is connected to E, so let's think about E for a second. What vertex is 3 connected to that 1 is not? It's 7, right? So this would be a 7 here. And you can kind of see now that I've gotten pretty far along on, so A, B, C, and D have to go to 1, 3, 6, and 8. We've got the A and the B going to the 1 and the 3. I haven't done C or D yet, but those are obviously going to be 6 or 8. Same thing here, 8 or 6, right? Whatever. So we're almost done. We almost have the isomorphism constructed. So let's think about C for a second. C is connected to E, F, and H. E, F, and H. So that would be 7, 5, and either 2 or 4. We haven't decided yet. So is there a vertex that, so again, we're starting with C. C is connected to E, F, and H. And so,
When you have to pick one.
I think
It's
we're,
like,
yeah.
or
just pick.
You're just gonna pick one because it's not gonna matter, right? It's gonna be like, there's some symmetry of this setup here. So you'd be able to, for example, pick 6 for C. Okay, great. I think I like that. So we'll just do that. Okay, so 6 and 8 are like so. Now that does not mean that you can arbitrarily pick these two.
No, that.
Now this will be totally dictated. So let's just see, let's see, which one would G have to go to? G is connected to A, B, and D. So A, B, and D is 1, 3, and 8. So which vertex is connected to 1, 3, and 8? 4. Okay, so that means that G has to go to 4. And that means by process of elimination, H has to go to 2. Guys, these are a little tricky sometimes. You actually can't really show a lot of work for these because, you know, there's not a uniqueness to this theta. There will not be only one right answer. And so at some point you do have to just make a choice. I'm going to decide to send A to 1 without loss of generality and kind of proceed as such. But yeah, this would be the kind of analysis that you have to do here. Yeah. So that one is, I would say, moderately difficult. There's, you know, obviously these can get pretty crazy if the graphs are really, really big. But that is just the nature of the beast. Okay, so we've done a few examples to practice. I'm trying to decide. Yeah, I tell you what, why don't we pause, and I've got a little group work here. I thought maybe we could practice. There's 3 more graphs that we can, 3 more pairs of graphs that you guys can test for isomorphisms with. Let's send this around and let you guys find some partners to work on these with. Kind of fun.
Yeah.
There's, pass those back for me if you would.
My entire group.
Your guys, end up here.
We still have
Where he would be. Wander around the room, and grab some partners and give it a try.
Let's go, boy.
Where are you working?
So.
But you gotta be ready for what, and then.
Ready for that now?
Yeah, somewhere down.
Yeah, so they published Thursday and like I really want to start 2 hours. Cause I have to give the other class until 6:45, so I'm like, do I just go and just watch the video later? Or have to do that or even. Yeah.
At least I have that.
Yeah, yeah. Can't decide.
Well, you got another week.
Yeah.
Okay, sounds good. All right.
It was really, I don't even feel bad, like.
Go
sad,
for it.
But it's just in
Teresa,
me
do you have
now,
partners?
so I'm like trying to talk to you.
Just wanna make sure nobody's alone.
You know what I mean? Actually, they, my voice is not like, I didn't make me. Oh my God. I can't just. Like,
Like 20 months.
yeah. I don't know. But it's okay.
Yeah, I got they're not. Oh, my.
I figured that's why.
And this one doesn't.
I hear. I remember what it was. I don't remember if she told me already before, but.
Oh, yeah, you gotta get. But right after this, I always.
No.
I'm like, no, it's wasting my time.
Yeah.
Yeah. When you go.
It's really hot in the degrees.
Hopefully it's okay.
So much. Oh, I did. It's just all like your entire class. It's a science. I think next time they do get me over this day. Yeah. They came up to me, starting to talk to me really.
Different, different disease sequences. Okay, that sounds like a good excuse. This one has three verses, this one only has two. Yeah, two. Yeah, that looks good. Okay, excellent.
It's like,
That look okay?
no one really asked me. They have much more period. Plenty of time to go.
Cycle, right?
But it's just, he's like, yeah. They're not- You know, saying, I was that. Kind of, but not like it's easy. Yeah, no, I really like. The team is maybe I will say it's bigger. So you do it basically. It's pretty almost.
No, I was just trying. And do the second thing.
He has for. Oh, but D has more.
Wait, but you're not.
So, no.
Yeah, it's coming along here. Okay, these are, this is a no because. Yeah, they're. They don't match. Because I think that I would be a little more specific.
Oh, yeah.
Recycle, okay. Okay, good. There's no recycle. Okay, that's crazy. That's exactly right.
So that they're both complete, but.
Johnson.
Every.
Every possible. Recycle, okay, I like it. If they're both complete, then they'll be nice and marked.
I don't think they're.
If I could. See.
You have to have every possible.
You'd have to have every possible. What's that? Yeah, the degree of each vertex will be in my.
Yes.
Yeah. Yes.
Every possible edge.
Which. So then if one graph.
Oh,
That would be, well, if that was true, you would just have different numbers of edges, so you would know that immediately.
All possible edges.
Unfortunately, that reason isn't gonna work on the sheet. Exactly.
Do you wanna count that?
Just, why don't you just mark?
and then now.
Both of eight. I think that's Do you want me to start? Okay. Everybody, go ahead. Okay, here we go.
Oh, I have a feeling.
Because
I have to like that every single cycle. I guess I was last one. The last one.
Because I both leave received. Great, and then now we got the.
Well, for all of this stuff. I fear.
But this one is what the
It's on this and wait.
where there's not.
Yeah. Right, so it's amazing. Oh, yeah, it's not right. I just gotta say, guys, the brightest.
I think it's just. It's like, that's just like a tedious job, you know, it's just like, he needs to like keep track of things.
So you have a lot when 2 grams are. But it's not gonna feel like you're.
Okay, so now we find a better place.
You said it's not that I'm doing the. You get.
No, it's not.
No, I think it is. Right. It's
But it's but when you.
Within the ones that are not.
Yeah. This like, can you get from 8 to 10?
Right, so, I would try to, there's one of the graph, and then complement edges.
Okay.
And then see, and do it for both graphs, and see, let's see what. Okay. Anybody need a hand?
They're trying to prove it.
For which one? That they are SMR?
Even like, what's the cost of it?
So many edges here. I'm kind of nervous I'm gonna miss something. This is too much, like, too much information. Do you remember how this worked? Probably. So the thing is, that they're assuming edges here, it's gonna be very hard to sort of. Yeah. But remember the edges.
When I was out, they were holding me to have the high time, so I have a couple of my. So eight of not eight, you're saying, oh, okay.
Not just think of it as actually draw. The draw. It's in the ground where you take it. Just think. And put in the ones that are missing. But you have to compare those. So you would do it for both graphs. And then compare the complement graph here to the. And make it easier to tell like those graphs now.
They're like.
So like you'll feel like. That, would you like that a different? Well, you got a different. I was gonna say, yeah, different colored marking. Great.
What we want to do is.
Right. I would be. There's a
But I don't think that's like, I don't think it's what a count that. That's kind of like, because you're saying like, it's like H will go to H2. I think if the graph was in a multi-graph, I think the loops, you shouldn't be like, or like. Is it? No, B is not gonna be. Or sorry, 8 is not. Sorry.
So one's not connected to this.
Okay, so.
Oh,
right.
It's one's not. Less. For example. Was a national. It's not number.
Yeah, okay, so now look at this.
I don't think it does.
You think over?
Easy money?
No, it
It's because you originally didn't have a. I think about, even then, like.
You would have brother. Runs for more time.
About this. Not really know.
I'm like, God. It's trolling.
Oh, please. Yeah. Really clever ideas. How are you guys? Did you figure this out? Or, and this is the compliment graphs, right? The compliment graphs are not IC32, so then that means the original graphs are not IC32. The other thing about this is you could also have said, this graph is not connected. It's squares. That have. But you could. Squares. This is not connected. This thing is totally connected as one giant.
That's like.
Your reason is great, but you can also look at it and you can take a look at it. They're really nice. Yeah, so I like that problem. They're using the complement graph as a trick.
A little confusing.
Yeah, so I mean, remember that I can redraw this. Redraw this. See.
Believe in you.
And G here. This is actually the same graph as that line. I've just moved the vertices off in places. So. Separate squares, I can't walk from this square to that square, there's no edge to my hair.
Okay.
Whereas over here, I can walk. I can get my standing over the vertex by just taking a walk along that big giant stars.
If that was not like connected, then it would be.
Then you might start wondering, so if they were both connected, if they both have all the same cycles, if they both have the same degree sequences, then you might say, oh, I wonder if those actually are isomorphic, in which case the original graphs would have been isomorphic as well.
My question was the opposite of that. They were both like not connected.
Yeah.
So it would still be. Right now, but we have two graphs that are also not connected.
Well, if they both share that structural property, then I don't know if they're isomorphic different. I
Oh,
would have to think about a different property instead. Until I could find something.
so that's not.
No, but you shouldn't do it that way though, I don't think.
Yes, so that's what.
I think.
I see. Edges. But that's also conserve none.
Yeah, there was a lot of different. Keep going back to them.
Some of those should then also.
We allowed our P of multi-class because you really want them.
Yeah. So what we can do is we can decide to scrap these or you can replace them with what is called their complement. So I stopped over this in my video. Idea here though, is that the two graphs are isomorphic, and so are their complements. Be there. And put in the ones that are actually. So I would grab a different colored marker. Let me grab you a different color.
Brandon, who would you draw? Oh, sorry. Draw them.
Can you draw on both graphs, draw in the red marker, the missing edges from each graph and then compare the red graphs? Or you'll have a red graph on the left and a red graph on the right. Well, then, does anybody need help?
Cause that's what it means, like. That's what we.
What's your idea?
But they all.
Uh-huh.
So we could repeat like.
Are those two guys? Have you guys figured what's the other thing?
That would, I would not.
Okay, you said the word.
Does anyone know how to like draw?
But if you said
What size set?
Yeah.
We would be, what we've been doing pretty much. I don't know.
It's always something that's good.
I was thinking of the extra.
Yes.
Yeah.
Yes. I've already figured out.
There's just like,
But it's, for me, set this up right. I know in the example.
Honestly. Just say that they're, I'm not supported. Somehow.
For the ones that we have on the left.
Gee, that's pretty good. Yeah.
That comes.
Huh?
So the two.
This is my competition.
What is going?
Bro, I need a new brain, like, I need some surgery, maybe. I need to.
Anybody have any questions?
We're just trying to figure out.
For number 3, or for number 2?
Only one way to draw. Multi-graph. Reverses and inverses. Well, I'm trying to we're turning the rock. I would like this to be a multi-graph. Yes.
Anything one single.
For an age. You know, how would this index or edges? So I think either extent looks like is, you know, like. But if I do that, then that's not. The decreasing is 4. I can't shit this guy's left out in the cold. If you try and can't face it anybody, you don't have a vertex. That's why I was trying to stay. There's only one way we can use it for races.
Yeah.
This doesn't.
Okay.
Well,
The loops.
We can do 3 and like until I can sit.
No, I was asking, like, all like, what is it? Like,
First steps.
Yeah.
Step 1.
Or we were taking-
Do we try?
So now there's only one thing left that might be. And that would be that would be 2 out of.
Yeah, so this
Two
one's like,
things.
like, these, and this one's
This.
like, well, like, thank you for using it.
This is the only way you can draw that graph. Such that the sequence is formed. That's basically it.
Yeah.
Yes, if you're at a G and a G. Yeah, I did 5:15.
Oh,
Hey, guys.
10 minutes.
I. Everybody got quite done with this today, but so if everyone needs to get a chance to totally finish, I encourage you to. Play with this a little bit on your own, later on, maybe over the weekend or something. And ask questions later if it's not clear in any way, but really good job today. You guys, good observations out of these graphs. And I will see you all in my office hours or Tuesday at the latest.
Oh, you're still myself.
all right.